Hey guys, this is Carl from University at Buffalo, and in this video, I'm going to show you how to use Markov chain Monte Carlo methods to tackle some actual problems. So one quick question here is that what is Monte Carlo? Well, it could be a beautiful city in Monaco, or it could be the name of a famous casino in Monaco. But it's also a famous simulation method often used in computer science, the Monte Carlo method. The general idea of Monte Carlo is that instead of solving the problems analytically, but we generate a lot of random walkers to simulate the model and optimize that to get a numerical result. And here let's take a look at a quick example of using Monte Carlo to get the value of pi instead of solving any lengthy mathematical equations. So as you can see here, we first draw a big blue square with a unit length, and then we draw a quarter of circle, and the radius of the circle is equal to the side of the square. So this quarter of circle is perfectly overlapped to the square from this side and this side. And then we start to shoot the random walkers, or you can just consider them as pebbles we throw in this square area. Okay, so this is just the first 5 pebbles we threw, and we can see 4 of them are in the quarter of circle area, and 1 is in the rest of the blue area. And actually, we will throw thousands or even millions of those pebbles, as you can see here. And then we find out that as we have more and more pebbles, then the number of pebbles in the quarter of circle represents the area of that circle. And the more pebbles we have, the more accurate result we have for pi. This is just the easiest way to illustrate the Monte Carlo, and I believe you now have understood how amazing the Monte Carlo city, casino, and the simulation method are. And the textbook I'll be using today, well, it's not a textbook, but it's even better because all the ideas and concepts and codes are included in one single Jupyter notebook. So this is the repo, and it's called Probabilistic Programming and Bayesian Methods for Hackers, and we'll be using the chapter 3 MCMC. And you can either git clone it into your local computer, or you can just copy and paste the link into a Google Colab, just like what I did. And then the only thing you need to do is literally just hit Shift and Enter. Okay, so now let's dig into this notebook. So first you need to switch the TensorFlow version back to TensorFlow 1. And then if you have issues with any packages, you can just use the following command to downgrade those packages. So we first use the TensorFlow probability to generate a uniform distribution for x and y variables, both from 0 to 5. And then we can see in the probability landscape, it's basically a constant because it's uniform distribution. And we can also visualize this in 3-dimensional. So it's like a top surface of this 3D space. So now if we use the exponential distribution for those variables, then we can see the prior landscape is not a constant anymore, but we have the highest probability around the 0.00 and the lowest at 5 points. That's due to the exponential distribution. And also in 3D, we can see this top surface is deformed from that constant surface. And we also would like to see what are the posteriors. So it's just the likelihood function multiplied by the priors divided by some normalization factor, but we can ignore in this case. So here we first choose a ground truth, that is one variable is equal to 1 and the other is equal to 3, as shown by this black dot. And then we use a Poisson distribution to generate a random sample that is 3, 4. then we can use that to generate the likelihood function, which tells us that given the sample we have 3, 4 here, then what is the probability to get our ground truth. And then multiply the priors to the likelihood, we can get this posterior landscape. And since in this case our priors is just a constant, then this posteriors is linear to the likelihood function. But in this exponential case, we can see the posterior is deformed from the likelihood by this exponential distribution. And since we only generate one sample, then it does not look pretty nice. So the ground truth is not pretty close to the posteriors. But now if we generate 100 samples, then we can see we sort of narrow down the final range of the result. And now in both cases, the ground truth is pretty close to the posteriors. So now we can use this method to actually analyze some data. So here we have a histogram of the dataset, and it looks like there are two normal distributions mixed up with each other. One is shown by the yellow line, and the other one is the green line. And of course, they have some overlapped parts. And we are trying to get all the information about those distributions. So the first thing we need to do is to make a guess about the probability for a single data point. So it's either belonging to the yellow distribution or the green distribution. And we can also guess the mean values or the standards of those distributions. So just by observing from human eyes, so one is probably about 120, and the green one is probably about 180 or 90. So that's the mean values. And for the standard deviation, for the standard deviation, it's not pretty straightforward, so we can just make a random guess, probably 10 for those two. So now let's see what we have for the results based on the Monte Carlo method. So we first have the traces about those walkers for the mean values and the standard deviations about those two distributions, or here we call them cluster 1 and 0. And we can see all of them are converging to a distribution of the possible results. And also we have the probability for data point belonging to the first distribution also converged to a certain range. And notice here for all the traces we have, we always discard the first 1000 steps because they are not particularly stable, so it's not useful for us. And then we make histograms about those mean values and standard deviations we have. For the centers of the distribution or the mean values, the first distribution we have is around 115, and the second one we have the center is about 200, which is pretty close as our initial guess. And for the standard deviation, we have about 25 for the first one and 23 for the second one, which is also not far away from 10, which is the initial guess. And we can also plot the probability for a single point that is belonging to the first distribution. So the red dots means it's belonging to the first one, and the blue dots means it's from the second one. And notice we always have some combined or 50-50 situations in the middle, and that corresponds to the mixture of those two distributions in a histogram. And finally, by averaging all the mean values and standard deviations we have, we can plot those two distributions. And if we compare that to the histogram of the original data, we can see the posterior's distribution fits the histogram pretty well. All right, here comes the wrap up. So we first use the Markov chain Monte Carlo algorithm to simulate the mean values and standard deviations for two normal distributions. And we also simulate the probability for them. And based on all the simulation results, we finally plot the posterior distribution and compare that with the original histogram, which fits pretty well. And if you look into the original notebook, you will find some other stuff, such as some rules about the posteriors and some tips for the initial guess. And it also teaches you how to reduce the autocorrelation to get a better convergence for MCMC. And for me, the most amazing part of this process is that all the steps and walkers and simulations are started from an initial guess. So please play around with his codes if you are interested in this method. And also, if you like the video, please hit like and subscribe the channel. And also comment down below if you have some thoughts. And thank you so much for watching and see you in the next video.